podium. My name is Stefan Hornemann. It's a great pleasure for me to introduce to you today's speaker, Mark Vogelsberger. Mark got his PhD in 2009 from the University of Munich, where he worked at the Max Planck Institute for Astrophysics in Aachen. He was a postdoc at the Harvard Smithsonian Center for Astrophysics and became Hubble Fellow in 2012. No, 2012. Since January 2014, he is assistant professor at MIT. Mark is a theoretical astrophysicist whose research spans from subjects like cosmology, galaxy formation, stellar feedback, and dark matter physics. He also is dealing very much with extensive numerical simulations, as you will see during this talk. Today's talk will be on the era of large-scale cosmological simulations, exploring large and small scales simultaneously. We are looking forward to your talk.
Okay. Thanks a lot. Thanks a lot. It's a great pleasure to talk. It's my first time. So before I start, I just would like to thank all my collaborators, and not just a subset of collaborators, and especially I would like to thank Dr. Spring, who's a long-term collaborator of mine, and essentially many of the results that you see here would not be possible without him, so really thanks a lot for that. And also Shai Ganel is a long-term collaborator, and also just so I will be talking about galaxy formation simulations, and specifically talking about simulations that cover large volumes and give you statistical power, so to speak, so statistical samples of galaxies to compare to the observations, and I will try to show you what we can learn with this and why we do this and what are the problems and what we might do in the future. So it will be a pretty general talk. So just to set the stage, the basic idea of what we want to do is with these kind of simulations, we want to understand how actually galaxies form. As you know, there are different types of galaxies: elliptical, spiral galaxies, irregular galaxies, small galaxies, large galaxies, and so on and so forth. So we would like to have a predictive theory that tells us how these galaxies form and what makes the difference between a spiral galaxy, for example, and an elliptical galaxy in the formation history. And obviously, we would also like to have a theory which is kind of in agreement with the observations. The framework with which we do this is the familiar with it is the Planck feature, the inflationary phase, and with a certain large fraction of dark matter and dark energy. So I guess most of you have seen this image in where you have Big Bang and inflationary phase, and cosmic microwave background, the first stars, the first galaxies, and so on and so forth. So what I'm mainly interested in is this more late time thing, so not so much the first stars or the first galaxies, but more slightly lower redshifts. And yeah, we would like to understand how this works, how the galaxies form, and the initial conditions that we have is just what we know from the microwave background. So these are the initial conditions for the calculations. And then we know that a certain amount of dark matter and dark energy, which then kind of is the backbone of this formation. So the galaxy formation problem itself can actually be summarized in a pretty easy way, I think. So as many of you know, dark matter is kind of the backbone of structure formation, and since the 80s or 90s we have now already better and better predictions of the dark matter distribution. And what we see in the upper right here is a follow-up of the Millennium simulation of Vogelsberger. It's the Millennium 2 simulation, which was led by my point question. You see the dark matter density distribution. However, the question then is, how do we get from this dark matter distribution to the galaxy population? And this is not such a trivial problem, because if you look, for example, at the halo mass function, which is shown here in this orange or yellow line, so this is halo mass and then number density. And if you look at the same time at schematically the stellar mass function, which is the solid black line, you can clearly see that they are not just scale versions of each other, but there's some apparently complicated nonlinear mapping going on between the two. Yeah, so if you look at this low mass end and the massive end, you see that there's just a suppression in the number density of objects. So it's not just a one-to-one correspondence between halo mass and stellar mass, it seems to be more complicated. And people have realized over the last years or decades is that what we think now is that so-called feedback processes, so there's a generic term of any kind of energy or momentum injection that you have to supernova or AGN feedback or AGN processes that actually regulate star formation. So we think that that's an important ingredient. So at the low mass end it's mainly supernova feedback, and at the high mass end it's the feedback associated with supermassive black holes at the centers of galaxies, which is EGM feedback. So the whole problem is essentially how do we turn this orange line into the black line. So that's the key problem that we have. And to do this properly, it's a rather complicated process because it involves a lot of physics and also a lot of scales. And so we want to understand this at the faint end, at the massive end, so we have to cover a certain amount of scales. So galaxy formation in that sense is a pretty complicated multiscale and physics problem. And that implies that you can do essentially very little on the analytically. So we have to go back or go to cosmological simulations, computer simulations to properly model it. And so what's the ultimate goal? Well, the ultimate goal is, as I mentioned before, is to have a predictive theory of galaxy formation. So that means you have a model, you put it on the computer, you make some predictions, you compare to the observations, and you see whether it fits or not. And this is how we refine the models further and further and try to get an understanding of what physical processes are important for galaxy formation. And I think nowadays we have agreed on a couple of kind of key ingredients that you need to make these kind of simulations successful, in the sense that they at least match to a reasonably large amount of observations. Yeah? So if you screw up the simulation in a significant way, you will not be able to do this, but if you follow more or less this pattern here, you can make pretty good progress. So the first thing you have to do is, obviously, you have to model in these simulations dark matter, energy, and the baryon physics. And although from the energy budget, this is by far the largest contribution, the complications and the multi-physics outcomes in this baryonic sector, which is a complicated part. And then on top of that, you have to include, especially for the baryon physics, then the relevant physical processes that shape the galaxy population. Now, this is a very vague statement because obviously a priori we don't know which processes impact the galaxy population. So this essentially works by trial and error. So we have an idea that a certain process might do something to galaxies, and we try this out. And then we see how much it does to the galaxy population overall. The third point that also became, especially over the last, say, 5 or 10 years, pretty clear that this is also important. You also need pretty accurate and efficient numerical schemes. So accurate in the sense that you want to have reliable results, that can be conversion results, but you also want to have efficient methods to essentially make sure that you can run with sufficient resolution and sufficient time scales on modern computers. And then to compare to observations, these last 2 points are very important. So to make a proper comparison to a circle like SPSS or upcoming SST, you have to have significantly large volumes that you simulate. And ideally, you also want those volumes at a reasonably large resolution, so you have a lot of statistical power essentially that you can study and then compare to the circles. And for the comparison, you ideally also want to have mock observations. Nowadays, it's not enough to run these simulations and just say this is the stellar mass distribution or the gas distribution, but you also want to have a mock observation which gives you, for example, an STSS runs how the galaxy looks like, and to directly compare to the observation data. And so I would say over the last decades, if you count also the dark matter simulations, this whole program has been extremely successful. So if you think back to the 80s or so, actually the dark matter simulations, these embodied simulations, were seminal to figure out that it's called dark matter and not dark matter neutrino and accumulators. So and so they have proven many times that this is a very useful and good approach to make progress. And so it's not surprising that these kind of simulations evolved a lot over the last couple of years. So this is kind of the newest law plot that shows you as a function of time the number of resolution elements. So this is essentially the number of particles you have in the simulation. So the more, the better. And what you can see, there's 2 lines here. This solid line, which is a best fit to the size of hyper simulations. So simulations which include also baryon physics. And then you have this dashed line, which are embodied simulations like the Millennium or the Millennium 2 or the Millennium XXL or any other embodied simulations. You can clearly see this is an exponential growth, and actually nowadays you can find dark matter simulations which go beyond the trillion particle limit. So really very massive simulations with a lot of particles. But you can also see that the hyper simulations are growing a lot. And the reason why I call the talk the era of hyper simulation or large-scale cosmological simulations is essentially because we have now in 2014, 15, and also 16 seen a lot of these high-resolution, large-volume hyper simulations, which are ideal to compare to observations like SDSS or upcoming observations from NSST. So I think this is pretty promising. And just to give you an idea how these simulations look like, so this is a movie from the illustrious simulation, which is a simulation that was done in collaboration with Volker, Lars, and Shai, and Dept, and many others. And what this movie shows you is that essentially a zoom in into the matter distribution, showing different phases of the matter distribution. So it started with dark matter, and now it's gas temperature. And you see here on the left the scale in megaparsec. And now it's the distribution of heavy elements. And the movie will actually zoom in onto a pretty massive disk or spiral galaxy, which you can see here. This is non-stellar light. And even this galaxy is still, within the simulation, extremely well resolved. So you can measure, for example, circular velocity profiles or velocity structure or density profile. You can all measure this very well. And something like this was not possible 10 years ago or even 5 years ago. So this is a pretty recent thing, which mainly has to do with the computing power and also the fact that some simulation codes like the one with Folger scale extremely well to these large number of cores to make this possible, essentially. Now, if you scale out here, you see the gas density now, and then you can appreciate the large scales that we have to cover. And now it goes to the gas velocity. Yeah, so the brighter, the brighter, the faster the gas, and now it switches back to dark matter. So that's kind of the redshift zero distribution of one of these simulations. Just let me spend a few words what goes into these simulations, so I will not go into any details here, but there are a couple of physical processes that we know now are important for these simulations, and in this model that we have for these illustrious simulations, kind of the minimum model that we think is important to produce a reasonable galaxy population. And most importantly, you have to have the supernova feedback and AGN feedback processes to regulate star formation at the low mass and high mass end, as I mentioned at the beginning. And then you have a few additional things. Obviously, you need star formation, you need some kind of chemical enrichment, and also UV background and heating cooling, obviously. And so this simulation was done with Flopper's code, which also helped a lot in various aspects of the accuracy. So this is kind of a minimal step. Obviously, this is not complete by any means, but it's kind of a set of processes that you have to include to get a reasonable galaxy population. So obviously, we are not the only ones doing this simulation. So this is another example from the Dept consortium, led by O'Shea, the Eagle simulation, which in terms of resolution and scope of the science and also the box size, you see the simulation data here on the upper right, it's very similar to Illustrious. It was done with a different code, and also the physics module, the details are different, but also this simulation is now extremely successful in producing realistic galaxy populations, and you can see some SDSS composite image of some galaxy in the upper right. So then there are other simulations, like this blue tide simulation, which was done in Berkeley. So this simulation is different from Illustrious and Eagle because you see it covers a much larger volume. It's half gigaparsec cube essentially, a bit more, and then the particle number is just enormous. It has a very huge particle number, which you need to get a reasonable mass resolution in this volume. However, if you have such a particle number, it's just impossible. It's very difficult to push this to redshift 0. So the simulation was actually stopped at redshift 8, because then it just gets too expensive to push this further. And so what this simulation is ideal for is, for example, exploring the first galaxies and making JWST predictions and many other things. So it's purely focused on the redshift 8. One problem, of course, is with these kind of simulations, if you stop them at redshift 8, you cannot make a proper comparison to observational data. So you don't actually know whether this model is reasonable or not, because we don't have too many constraints at redshift 8, 9, and 10. So this is one problem of this kind of approach. Another simulation which just finished, or which was published just a couple of weeks ago, is the Horizon AGN simulation, which is again rather similar to the Illustrious and Eagle. It's also run to redshift 0. It has a volume which is comparable. The mass resolution that I state here, the number of particles, is not fully fair because it's an AMR code, so this is a take with a grain of salt, but the mass resolution is approximately 10 to the 7 solar masses. And also this simulation is reasonably successful in producing a reasonable galaxy population. So I give two references here, 2004 and 16, because in 14 they published a high redshift result, and obviously it took them some more time to get to redshift 0, which is why this 2016 paper And this is the illustrative simulation that I mentioned before, which was done with Volker and many others. And you can look at the simulation data, it's rather similar to the Eagle simulation, for example. And also we get reasonably good galaxy population. So just to give you an idea about the time distribution, so this is it's hard to see this movie, but this is just from the illustrative simulation showing the dark matter distribution in a small subvolume. And on the right, you will soon see the gas temperature. And the redshift is running here. And so this whole cube that you see here has just a set length of approximately 10 megaparsecs. And what you see at early times, like redshift 3.5 or so, the gas distribution is still nicely following the dark matter. Yeah, and then you see at the centers, you see these reddish things, which is when the gas heats up. And then you see also this flickering, which is actually radiative feedback. And as time goes on, you also will see some kind of explosions at the centers of these halos, like this one over there, which is actually radiomorphic AGN feedback, which I will come back to this later during the talk. And what you realize is that this AGN feedback and also the other feedback process is essentially reshuffle matter distribution, so at later times the gas doesn't perfectly follow anymore the matter distribution. So there's actually also an interesting back reaction of the gas distribution on the matter distribution because we reshuffle due to this feedback to some degree the full matter distribution. Okay, I will stop this movie here, but you can see already now that the gas is pretty much heated up and also distributed kind of in detail differently from the matter. Okay, so that was kind of an overview of what we can do these days, and so I will now talk about first about the successes of these simulations a bit more quantitatively, and then also we'll talk about the failures. And a big success of these simulations is actually that we get now, I would say for the first time, kind of reasonably looking galaxies. Like if you go to the literature and look for like simulations producing late-type spiral galaxies, like 5 or 10 years ago, it was a big problem. In zoom-in simulations, and simulations which focus on a single object are very difficult to do this. But nowadays, we can actually, with these zoom-ins, obviously, but also with these large-scale simulations, we can produce thousands of pretty realistic spiral galaxies, like those ones on the left here, which are all from the electro simulation, and on the right, some elliptical galaxies, which also are kind of properly quenched, more or less the right colors, and something like that really was just not possible a couple of years ago. The main reason is that we have just better resolution, the physics model is also improved, and we also, I think, understand better the accuracy issues with various parts, and that all helped essentially to make this work with us. Again, we are not the only one getting this right, so this is illustrious, and then Eagle. They use different color scheme for the images, but you get the idea that also they get a reasonably galaxy population, and also the horizon AGN simulation produces some diversity in the simulated galaxies, which is, I think, also pretty nice that different simulations also really reasonably well. You can also quantify this a bit more. So what this plot shows you actually is as a function of stellar mass, the fraction of late-type galaxies shown in blue, the solid blue line, and early-type as solid red line. And you see this well-known trend, like if you go to higher masses, you are more dominated by these early-type galaxies, like this one over there. And the reason for this is that AGN feedback just scales essentially the black hole mass to some degree, and since the black holes are more massive in these galaxies, you have more feedback, and you can more efficiently quench star formation. And so galaxies turn red and elliptical, whereas on the faint end here, something like star mass times 11, you really have a significant population also of these star forming these galaxies. If you compare this to observations, which are these data points here, blue and red ones, obviously there's no perfect agreement, but again, qualitatively, we get these counts essentially right. Now, you can not only compare to the observations to the simulations, but you can also compare the simulations among themselves. So this is a plot from Frank's paper from his book simulation, where he showed the UV master function at redshift 8, 9, and 10. And for the panel here of redshift 9, you can also see the illustrious data, which kind of essentially lies on top of their simulation result. So there's also, it's not that these simulations predict now dramatically different results, so there's also a pretty good agreement between the simulations. You can also look at this at redshift 0, so this is a plot from the O'Shea showing the galaxy stellar mass function. Again, with some SDSS data here, redshift 0, and showing different results. And although there's more diversity of redshift 0, which kind of makes sense because of just a lot more nonlinear evolution going on, but also here I would say if you take only into account the simulations from the last 2 or 3 years, that ultimately most of the simulations look pretty well here. So I think we are now at a point that there's a pretty good consensus that many of the simulations are able to produce these kind of reasonably looking galaxy populations. Of course, there are problems in the simulations, the details, and also somewhat severe issues, but the basic properties seem to work out in many of the simulations. You can also go to a higher redshift and look at the stellar mass function, not only in redshift 0, so this is work from Heidelberg, where here, this is from the Erasmus, where the solid lines show the stellar mass function from the simulation, and then these symbols here are observations. And I will not go into detail here, but you can also see that the trend works out more or less reasonably well. Again, it's not a perfect fit, but we get the trends qualitatively right, and also quantitative numbers are more or less okay for most of the projects. Another thing that became very popular along these lines is comparing the simulations to what is called abundance matching. So the idea here is that you run a dark matter only simulation, and you have something like SDSS, and you rank dark matter halos and galaxies in the survey by stellar mass, and then you just try to figure out what is the typical stellar mass for a halo of a given halo mass. So you plot halo mass in here essentially on the x-axis, and then you plot the fraction of stellar mass in these halos. And what people have found many times, and this was done many times over the last 10 years, is that you get this kind of shape. So if you look at the sine line, it seems to be that star formation is most efficient at mass scale around 10 to the 12, and it becomes less efficient towards lower masses and less efficient towards higher masses, which again is essentially driven by, or we think it's driven by stellar field activity. And now the question is, can you reproduce this with the simulations? And also this works now reasonably well, so the black and the red line are just two slightly different versions of the illustrious results. And also here you see that the peak essentially at the right mass scale. It's not a perfect agreement here, but it also works reasonably well at the train and at the mass scale. So this is also a pretty good success. Another nice thing that you can do, especially with these large scale simulations, and I think here they are really ideal, is that you can explore environmental effects. So I'll only mention this briefly here. So this is from SDSS, a plot from Peng et al., where they showed the right fraction in this two-dimensional space of mass, stellar mass, and galaxy overdensity. And you can clearly see here this mass crunching along the x-axis, which has to do with ADN feedback, and along the y-axis you see this environmental crunching, which has to do with the effect, for example, if you are satellite and fall into a massive cluster, for example, you experience ground pressure stripping and tidal forces and so on and so forth. So essentially also get quenched by that. And then you get this pattern here. You can do the same exercise with the simulations, and although again quantitatively it all doesn't work out perfectly, but you get again similar trends essentially with the simulations. And I think for these kind of simulations are ideal because you can essentially not do this with zoom-in simulations only because you need the large scale environment and you need a lot of statistics to make these plots. Okay, the last thing that I want to mention before I come to the failures is you can also make these mock observations now to very practical precision. So this is an example of Greg Snyder essentially, which was published in this paper here. So this is the HST Hubble ultra deep field, and on the right he made a version of that from our simulation. And if you run statistics on that, like looking at the sizes, the colors, or the distribution of the galaxies, you would actually recover that they look very similar. And, so which is also a big success because that was not possible before. Okay, so this was all about the successes. So obviously there are also problems in these simulations, and the problems are actually the interesting part of the whole thing because only through the problems we can actually make progress. And I will now pick one problem of illustrious and just show you what it is, and then potentially also how to work with this. So this goes back to a plot from Heidelberg, which he had in his 2014 paper. And so he looked at this plot here, and we should only focus here on this green solid line and the green data points, the rest is not so relevant. So what this shows you is, as a function of halo mass, the fraction of gas in these halos. So these are the data points that we have at this mass scale here, and the solid line is what we measure in the simulation. And this is kind of a linear scale, so it doesn't look too problematic, but essentially we are quite off here at the group and low mass cluster scale with the gas fraction. So really there's something going on. And the reason why this is, for example, problematic is if you want to make, for example, SC predictions or X-ray scaling predictions, they are all pretty much off because of this effect, because you just don't have enough gas in the halos. So it turns out that this is actually an artifact or a problem of our AGN feedback that we employed there. And you remember maybe this movie that I showed you in the beginning where you saw these massive explosions. So these explosions, which are related to the AGN radio mode feedback, they drive out a lot of gas from the halos beyond actually the radio radius, so you really reduce the gas fractions a lot. And that is actually what's happening here. So you have a lot of radio mode AGN feedback happening here, and a lot of the gas is just removed. And that's the way how Elastos essentially quenches star formation. But that's unfortunately the wrong way, because nature apparently doesn't quench by removing gas, but it just does it in a different way to keep the gas fractions high but still quench star formation. Yeah, so this is quenching for the wrong reason essentially. So possible ways out are that one has to modify the AGN feedback in some way, and there are some suggestions here, like you can think of making the AGN feedback less bursty so that you have not so extreme explosions that I showed you before, which is related to the duty cycles of the AGN, of the accretion process. You can also think about coupling the feedback differently into the simulation, like doing this more like in a kinetic way, or you can think about something completely different. You can think about non-thermal pressure sources or cosmic rays or anything else. So there's a huge diversity of what you can explore, and obviously all these things that we explore are kind of phenomenal. Yeah, so we are far away from resolving any of the detailed AGN or black hole physics in these simulations. So to give you an idea, I just want to show you on a few slides what actually happens if you change the AGN feedback. Yeah? And I will do this for 3 models. So model 1 is essentially the Elastos model, which is just a slightly modified version of the model of the Rasiachi. And this is essentially a model where you have the halo of the black hole, and then you dump a lot of energy in kind of a spherical region, which then drives these enormous outflows. Model 2 is a model that was used for some liquid simulation by Federico and also by Frank et al., where it's similar, but the energy is kind of distributed more in a smooth way and it's less bursty, so you avoid a lot of the problems that you have in Model 1. And then Model 3 is a new model of Heidelberg that he developed with Volker, which is based on more kinetic approach with momentum injection, essentially. Yeah. So, again, all these models are phenomenological, but you will see that they are lead to quite dramatically different results. And one way to see this is in this plot. So this is a work from a paper by Christina Popper. So she actually simulated 6 clusters spanning mass range from 10 to 13 to a few times 10 to 15, so from the group scale to the massive cluster scale. And what she then did, so these are these data points here, the different clusters for the different models. She then measured the gas fractions. And the only takeaway of that plot is that the blue line is fit to the blue data points, and the blue data points are the Elastos models, so you have again this issue of these low gas fractions like the normal stuff. This is not a problem for the other models, yeah? So for this Elastos TNG and the Auriga model, these green and red lines, this does not happen, but it's clearly an issue for the Elastos model, which again is related to this very bursty nature of the AGN. And as I mentioned before, this has also implications for observables like the X-ray scaling relations at the faint end are pretty much off, and also SC scaling relations are pretty much off. However, if you look at the most massive end, actually all this doesn't matter that much anymore. So if you are above a few times 10 to the 14, then the gravitational potential is so deep that AGN cannot screw up the result completely. So then essentially you see that the data points are the simulations here really reasonably well. But for the group scale and low mass cluster scale, there's really a problem with this of AGN. Yeah. Well, that's true. I mean, this is just in this version, so we have an updated version of the address. So there's also the X-ray, you have data points here as well, which I just didn't have in this version. Not sure, probably not so much. But for the X-ray, you have okay, and this observation effect, you can also see this if you look at the gas distribution or the temperature distribution. This is again a quote from Christina. So this is showing gas density for the 3 different models here. So it's the lustrous, the old model, the bursty one, the THG model, the kinetic one, and this more smooth one, the Auriga one. And this is a cluster which is 3 times 10 to the 15. And if you just look for the gas within the real radius, it all looks pretty similar, so there are no differences. But if you go to the group scale, you see this deficit of gas here, which was just blown out by this OAGM feedback. And if you look at the new models here, these two, you actually don't see this deficit. So that's another manifestation of the issue that I mentioned before. And just the last thing, now with this new model of Vogelsberger, this works much better now. So just 2 things that I want to highlight from my next paper, which should be in the archive tomorrow. So one thing is that if you look at gas fractions here, so this is the plot that I showed a few times, you can clearly see that there's this upturn and disagreement with the data for the peaks and low mass clusters, so that seems to work very nicely. And at the same time, if you just focus here on the red data points on the red histogram, you also get a really nice, a better color quality than we got in the old simulations. So it doesn't really quench, you can also see this in a bit more detail, but it doesn't do it by exploring the gas. Instead, it just drives essentially turbulence in the center into the star formation range and momentum totally wrong. Okay, so that was one of these failures that you cure, and then you just have a better model and you go on. But obviously, as I mentioned before, there's also much more physics that can potentially go into the simulations, which we didn't cover in the old models and we still cover in the simulations. And I just want to present 2 or 3 things about this and just show you what you can do with this. So the first thing is work that I did with Federico and Federico Pacmo here at HITS, which is actually exploring large-scale magnetic fields. So what you see here is uniform box simulations, again, first without any feedback physics, so including the star formation, and then another simulation which has this old lustrous physics in it, and then this is coupled to an ideal machine implementation of Vogelsberger. And what you can see here is, don't see too much, but the clear effect that if you have this gas cooling and compressing, you just get these large magnetic fields. So that's the only thing, the only takeaway message from this plot. More quantitatively, you can then also look at the magnetic field strength in microgauss here as a function of halo mass, different redshifts. And one thing you notice here is that this is monotonically increasing, which is not too surprising because you go to deeper potential by higher densities and more turbulence in these systems, just have more amplification of the field. But then you also get this kind of plateau value, which is in the most massive systems that we could simulate with these boxes around 10 to 30 microgauss. And this raises immediately the question, how realistic is this, or how does this compare to observations? And to do this, you can actually make Faraday rotation maps. And this is done for the 3 most massive clusters that we had in these simulations. And so this is Faraday rotation in one or the other direction, this is where it's red and blue. And this is kind of the scale. And as I said, these are the 3 most massive clusters. And then you can try to compare this to observational data. So this is shown here. These are essentially spherically average versions of these maps. So the black line is the simulation result, and then the red colored symbols, and also black symbols here, are observations. So obviously there's a lot of scatter in the observations, but at least you see that in the centers and also in the overall shape kind of works reasonably well with the simulation, which implies that the magnetic fields cannot be completely off, otherwise there would be a severe problem with these measurements. Another thing you can do with MHD, which is kind of interesting, is that since we are doing ideal image simulation, we have to put a seed field in the simulation. And as you know, in nature there are many competing theories how the seed fields or where the magnetic fields come from. And so the idea is whether there's any impact of the seed field on the galaxy population of data redshifts or lower redshifts. So for example, if I have a certain seed field of some nanogauss, will this change my galaxy stellar mass function in any way? And the canonical argument is no, it doesn't, because you can take a very small seed field and then you go through exponential growth and it's not very sensitive to the seed. However, you can analytically work out where this argument breaks down. So if you will have magnetically dominated gas flows, so if you have homomorphic seed fields of the order of 1 to 10 nanogauss, that you can analytically show. And in fact, if you explore this with simulations, you can also see this. So this is another plot from a letter from Federico. So what we did here, we changed the magnetic field strength from 10 to the minus 12 Gauss to 10 to the minus 8. which is in this regime where it becomes important. And you can clearly see that both for the galaxies that are mass function and also for the stellar mass with the same mass rotation, you get this suppression essentially because of the magnetic pressure. And furthermore, you can also look in low-density regions, for example, where evolution is still pretty linear, where you also preserve then the field topology. So this is a simulation where the field initially goes in that direction, and then you measure this at redshift 0, you preserve this, and you go in that direction in the y direction in the second plot, and also there you preserve this. So potentially that could to some degree be used to, especially this, constraint fields further, because if you look at the constraints in the literature, they are all in this ballpark essentially what is possible. If you look at Planck or so, this is kind of the area where the quantum constraints are. So it's not outrageous to have these secrets. So this is, I think, an interesting thing that you can do with NHD. Obviously, especially this rotation measurement could give you an idea of additionally constrained galaxy formation. Dynamically, for most of the regimes, they are not so important, at least for these kind of simulations. But I think an interesting additional thing that we should explore in these simulations and predictions, especially for refinements, for example. Another thing that I would like to briefly talk about is another project of a student of mine, Brian McKean. So he worked on the implementation of cosmic dust simulations. So cosmic dust, essentially in all these simulations, cosmic dust is always neglected because it's a tiny mass contribution, and it's assumed that for the large-scale structures it doesn't matter at all. But nevertheless, we wanted to try this and see what we get. And so what he then did, he implemented a very primitive dust model in Navier, which takes into account 3 processes. So it has dust production, it has dust growth in the ISM, so if you have gas phase atoms colliding with existing grains, and it also has dust destruction in the ISM through shocks and also thermal sputtering. And this is all done in a super simple way. But nevertheless, if you look at it, you get some interesting results. So this is a movie showing the formation of a Milky Way-like galaxy where I only focus on dust and metals, and also the left here shows the dust density, the intermediate here shows the metal density, and then you see the ratio on the right. And one thing you realize is that actually the dust to metal ratio that we predict here is not uniform about spatially. So there are actually 2 order of magnitude variations in the dust to metal ratio in the disk and also close to the disk. So this canonical idea that dust follows nicely with the metals is actually in this model not working out very well. And simply because it's probably not a good approximation. And we are pretty confident that the model is kind of working reasonably well, because if you look, for example, at the dust mass function here, so this is observational data by points here, and the red is the simulation result. So you can see that this actually fits pretty nicely the observed dust mass function. So that means, although the model is simple, it cannot be completely wrong. And the same is true if you look at the cosmic dust density. So these are measurements, so these are pretty uncertain. And we should only focus on the blue line. The blue line is a prediction of the model. So clearly we get some plateau here. It doesn't have the exact right amplitude. The only severe issue that we have that we don't have this drop here. However, there are data points here and there, so it's also not so clear whether this should really happen in the data. But qualitatively, again, the trends I think are working at the moment. Another thing that we explored just now, so this is very preliminary, is the impact of dust cooling. So over the dust cooling, especially in high temperature gases, is especially important for supernova remnants. So if you have in the ISM supernova going off and produce a lot of dust, then dust cooling can become very important because you have a lot of dust at high temperatures. And if you look at this cooling curve from Australian silk, which shows as a function of temperature the gas cooling as dashed line, and the dust cooling as solid line, you can see at high temperatures there's an enormous contribution from dust cooling, which we typically neglect in our simulations. Now, the argument why people say that might only matter for supernova remnants and these environments is that you need a lot of dust. And if you go to a halo, like a cluster, and although it's enriched with dust, the ICM, it's just not clear how long the dust can survive, because if you have high temperatures, then also the sputtering of dust is very efficient. The time scales are typically about a shot. So the question is, can dust cooling compete with the sputtering in any way to make a significant impact? And so what we did is we looked at, I think this is actually 2 for 1.5 at one of our clusters, and we just measured what we get in terms of cooling contribution. And so this is showing as a function of fraction of real rays, the contribution of primordial cooling, of metal cooling, and dust cooling. You can see in the outer parts there is some dust cooling contribution. So this is super preliminary, that might change a lot, but at least at this stage it seems that dust cooling does something, and we also did some preliminary analysis of these ones, and indeed you seem to affect a couple of things in the clusters, like the gas mass is affected, the clusters that can cool down, also vacuum masses are affected, and many other things if you include this dust cooling process. So that's something which I think is interesting and could turn out to be important, especially if you look at SC or actual scale relations, how this would impact the results. Okay, so for the rest of my talk, I just want to talk about things which come next. Obviously, this is a very subjective thing, but so these are some projects that Volker, Lars, and we are working on. I'll just present 2 projects here. And the first project is a project which is led mainly by Volker, Lars, and Dept at NKIA. So this is the follow-up of illustrious, essentially, using this new model of Heidelberg that I just presented. So the idea here is to first repeat essentially the illustrious simulation, which was this 75 megahertz over H, so approximately 100 megahertz box, with this updated AGL model, and also with some improvements in the stellar feedback, plus including energy effects, a few other tricks. And that simulation is close to be done, and this looks already extremely promising. So many of, especially this AGM problem of illustrious does not exist in this model anymore, in this simulation anymore, because there was this update of the AGM model. And then there are also plans to run a larger volume and also a smaller volume. So as you can see, this is a lot of computing time, and as I said, this is mainly done by also Rüdiger and Volker. So why is this so exciting? Well, because as I said, this new model of line really improves a lot of things. So this is also taken from this paper, showing you the balance matching plot. So with this retuned wind here, you get this significantly better agreement at the tank end, and also with the AGM model, you get a very nice agreement of the stellar mass as a function of air mass at the more massive end. So I think this is really a substantial improvement, and especially for the massive end, we'll turn out before. So if you want to do statistics on the C effect, actual effect, so actual scaling relations, this is really significantly better than the old simulation. Another project that I would like to mention is a project that we do at MIT, again with Christoph Honger and also with Volker Springer. This is so the idea here is to explore the ICM of clusters, so pretty high resolution. So this is led by Raoul Kaman, who's a postdoc at MIT. So what we try to do here is to understand the impact of anisotropic thermal conduction on the ICM of clusters. What you see here is a 6 times 10^14 cluster. You see the gas temperature, gas density, and magnetic pressure. And the upper version has no conduction at all, and the lower version has this anisotropic conduction included. And clearly you see this typical effect that you expect, that you smear out small scale temperature fluctuations here because of the diffusivity that comes from the conduction here. What is more interesting is if you then compare this to isotropic conduction, you get a significantly stronger effect here, which is not too surprising, so it's much stronger. But what is even more interesting is that if you look at the Mach numbers here of this halo, as a function of radius for a run with anisotropic thermal conduction and with no conduction, so if you just have to look at the red solid and the blue solid line, you can clearly see here an increase in the Mach number, and if you look at the turbulent pressure, you see then is that you also get an increase in the turbulent pressure here. And so these are pretty recent results, so it's very preliminary, but it could be likely that actually some of these instabilities, like magnetothermal instabilities, are actually acting in the center here to generate turbulence by this magnetic plasma here, essentially. So that's kind of something we're currently exploring. And although this sounds more like academic exercise, this actually also has an impact on the Faraday maps. So if you do them again now for these different situations without conduction, two different versions of conduction. You again, so this is a power spectrum essentially, and you also see some differences in the structure of these paradigms, which we are currently exploring. Another thing that might be important in that context, which we haven't checked yet, is that also the bias of these clusters might be affected by additional thermal pressure, turbulent pressure, which is also then potentially driven by these instabilities, but that is something we still have to check. Good. So I will now conclude my talk, and I thought instead of giving a conclusion, I will discuss a few open problems, or just an overview of problems that we have, I think. And I came up with 4 different categories. So the first category that I would like to discuss is the barrier physics, and so obviously, there are a lot of physical processes that might impact galaxy formation, like the small scale ISM physics, how important is radiative transfer, the details of AGN and black hole physics, also magnetic fields and cosmic rays and so on. So these are all processes which to some degree will affect the galaxy population. And many of these processes have been explored, or are currently being explored, on small scale simulations like detailed ISM simulations or isolated galaxy simulations. However, I think to make really proper connections to the observations, you need to connect them at some point to large-scale simulations. And that probably will require a significant retuning or coming up with new effective models for small-scale physics and large-scale simulations. And the reason why I think this is interesting is that the current simulations that we have to give a pretty reasonable, as I showed before, match to the observations. But all our models, like the AGN feedback, the stellar feedback, it's all just super phenomenological. So we don't know exactly how stars form, we don't know the black physics in detail, but nevertheless, these simulations give a reasonable galaxy population. So there's something in these effective prescriptions which kind of is already sufficient to give you that. Yeah? And I think you need to understand better this gap between the small and the large scales, and obviously. I'm not saying this so everybody agrees on that, but I think there's really a lot of work that needs to be done on that front. The next point that I didn't mention at all during the talk is that the whole talk I actually assumed that numbers here are just by theory. So we believe that dark matter is cold and collisionless, and there's dark energy, and energy is just a constant energy density probably. But this is by no means guaranteed. And many of you, or all of you, are familiar with all these small-scale CDM problems, like which started in the 90s with the missing satellite problem, then the core cost problem, and now the clear problem. So there are all these kind of problems. And so people are working a lot on alternatives, like dark matter was very popular at some point. Now L7 I think is a bit more popular. And of course you can also throw away the of gravity and about modified gravity or R or whatever you want. The problem with any of these approaches is that we have only a limited amount of CPU time, so we cannot explore all these models. So I think what we really need is kind of a mapping from, for example, if you have particle physics models for that matter, you have to have effective mapping from all these microphysics to effective structure formation problems. For example, many of the structure formation simulations, or structure formation in general, doesn't care about every detail in the particle physics sector. So most importantly, you care about, for example, the actions between dark matter or the initial transfer function and these kind of things. So we have to have a model that actually reduces all this microphysics space to effective structure formation models so that we can explore all these problems in an efficient way in the non-linear machine. And I think this will also be important in the future to actually explore more of these SEM alternatives. And the third point, before I come to my last point, is actually that I think also simulation accuracy is an issue, and by that I do not only mean the accuracy of the Heidelberg solver, how we do things in detail in the code, but also just the pure fact that we are watching an observational regime where we need, for Euclid, for example, theory predictions of your accuracy for the weak dancing, for example. Now, if you take the variable physics that we have in these large-scale simulations, and specifically the AGN feedback, for example, you get easily uncertainties of 10, 20, 30% just by changing the AGN feedback. And it's unclear how you can actually get this required precision to properly evaluate all these upcoming surveys. So I think we're now at the point where the surveys and also the observations data is significantly more advanced than the field prediction, so there's really a lot that needs to be done there as well. And the last point is not, the last point that I want to mention is not simulation accuracy, but it's simulation efficiency, and so I think this is also an extremely big problem. So as many of you know, the computational field, the whole field is potentially moving to access-free computing, but most of the codes, especially in our field like galaxy formation, don't even deploy petascale machines at all, and so it will be algorithmically extremely challenging to go to these millions of CPU cores. And you know, like I'm not an expert in that, but I can. So my feeling is, at least in the field of galaxy formation, there may be 2 or 3 people, and one of them is Volker, who can actually at all. So I think over the next years or 10 years or so, this will potentially also become a problem. And also, the amount of data that these simulations generate, which also approach the data packaging, becomes difficult. So that's a similar problem in observational campaigns like 20. The end of LSST will also have generated 150 or 200 petabytes, so we all run into these problems. And then I think there's really a problem because it's just a very small number of people who can actually do this. And I think these are kind of the challenges that we have. I think also.
Yeah, thank you very much for this very nice talk on the status, the outlook, and the problems of current cosmological simulations. I'm sure we have questions.
I can chat. Great talk, thank you. You highlight a couple of very important and interesting problems. In thinking on the first one, to truly get a fundamental physical understanding of the baryon in physics, you need to cover orders of magnitude and dynamic range that are just well beyond the scope of what we can do. So, in a way, it needs to remain phenomenological over the next decades.
Yeah.
So, in terms of improving, say, the phenomenology, where do you see the most important improvements will come from?
Well, I can just give you an example of what was recently done, which I think is a good idea. It's not super original, but it's a good idea. There was maybe many of you have heard of these fire simulations of the Hopkins, and probably have a set of people which is more small scale and more explicit than many of the other treatments that we have. And so what they did in one paper is they looked at the simulation of different mass scales and measured the effective mass of different winds. Right? So what we do in these simulations, and many other people do this as well, the mass loading for winds is an input into the simulation. So, and you know, the way how we explore this then is we know that we want to reproduce, for example, the galaxy stellar mass function at 0, and then we know we have some energy constraints on the wind, and we just kind of do primarily such to get a reasonable fit. However, you could also do this differently. You just look at these small scale simulations and look what they tell you what the effective mass load should be, and you kind of put this into the result. And there was a recent paper, I think a month or 2 ago, by Dept who actually did this, and you get pretty reasonable agreement with the stellar mass function. So I think this is, this is a very simple example. It's one example where you can actually make some progress. I mean, another thing is, for example, the wind tracking that we do is, as I said, very simplistic, but the wind itself can be a rather complicated thing. It can be multifaceted, can be complicated, some grays or other things. So I think another area where you can make progress is if you try to learn about properties of the wind, it's long or what the different aspects are, and just also factor this into these simulations. That you're right, we will never, for the future, not be able to do this properly in these large-scale simulations, but I think there's a lot of value in these small-scale simulations to just infer what we should do in the large-scale simulations. And unfortunately, if you check the literature, this doesn't seem to be such an appealing topic to work on because there's not much work done on it. Because many of the simulations of the models in universes go back to work with Volker, which is 10 years old. At some point we should probably update this for the most recent things.
Other questions?
relatively strong and saturated magnetic fields in primordial galaxies. But the question, I think, that you address is how to make them large so that they fill the space in between the galaxies in large galaxy clusters. And here my question is, are these then fields that come from the galaxies and are simply driven out by feedback, or are they generated by the turbulence you have through accretion shocks, or do you know where they come from on large scales?
So are you referring to this primordial?
Well, you show Faraday rotation measurements.
Yes.
And you take the intergalactic gas in these clusters.
This one.
And it seems to be strongly magnetized. And the question is, where do the fields come from?
Yeah, to be honest, for this particular study we haven't checked it. I mean, I think, the fact that this plateaus here, for example, it seems to indicate, that you see this plateau here. So at some point it becomes, I think it's largely driven, but I cannot tell you for sure, it's largely driven by the gas that comes in, generates a lot of turbulence, and is also compressed, and then it reaches a certain maximum. But whether it's not gas or within the galaxies, I don't know, I will check this in between. But this is something I think we also discussed with Rüdiger at some point, where they can actually through feedback lower our magnetic fields in the, maybe even in the IDM, just what you would get there. But yeah, one problem why it's not so easy is you cannot really trace mass so well. So we have these tracer particles, you will need to go to the analysis of tracer particles. So it can be done, but clearly it's an interesting question. Yes.
If you concentrate field lines in the galaxy, then you can out very quickly. I think that would be strong.
Yes, that would probably be possible. I'm just not sure how noisy the signal would be. Yeah, that would be the first one.
Other questions? What do you expect for further observations in the future for which you want to compare your simulations with?
I think what's, especially for the stellar feedback and the sliding of winds, which would be very interesting, or which is interesting, is this whole business of CGM observations, where you can really probe to some degree at least statistical properties of the wind. And I think that is important to characterize the thermodynamic state of the winds and so on, because as I mentioned a few times, we just try the winds in a phenomenological way, and it's very successful in the way that it reproduces the galaxy properties, but we don't know what actually drives it. Is it now mainly stellar feedback, is it rotation pressure, is it cosmic rays? And I think if you explore all these different possibilities, they all might lead to a different, for example, CGM observer signature. I think they're the observations, that's the closest that we can do to analyze the wind structure.
Any more questions? We will not have dinner with the speaker today, but Mark is here until next week at HIT, so if you send him an email if you want to have some question, if you want to meet him. Otherwise, I also thank you very much for your talk.
Thank you.